Okay, so in each equation, we are writing what expression A has to be to make the equation true. So table 3, what does A have to be in the first one to make it true? All right, class, do you agree with that? So let's see what it looks like substituted for the A. Right? Are these equivalent to each other? So then, yes, A just has to be X in the first one. Table 4, what about in the second one? What does A have to be? Okay, so let's see what happens if I plug it in for the A. Anytime you're plugging in, you should use parentheses, so notice I did that up here. If I plug in what table 4 said, is that the same thing? Do they mean the same thing? No, because technically I would have to, like, if it's set up like this where the exponent is outside the parentheses, I would have to then do 3x times 3x times 3x times 3x. That's what this squared would be. So class, how can I adjust it to where it will actually be equal? What needs to go for the A to make it 3x, just 3x. Then if I do that, if I plug it in, it even looks exactly the same down to the parentheses. Although you saw like in the first one, without the parentheses, it still means like the same thing. So in the second one, A has to be 3x to make it true. Table 5, what about in the third one? All right, so let's see. If I were to plug in 7x for the A, are these two expressions equivalent? What do exponents tell you to do? Sorry, one more time. Multiply the base by itself. So that on the left side does expand to 7x times 7x. So it's just another way to write it. This would be like considered like the condensed form. But it is true. So this is correct. If A was 7x, then it would make it true. Table 6, what about the last one? What does A have to be? Yeah, table 6, what does the last one have to be for A? All right. So if we plug it in, and anytime we plug in, we should use parentheses. Are those equivalent to each other? Okay. Remember, exponents tells you to multiply the base by itself. So this would be 5x times 5x, which you can simplify further. What's 5 times 5? What's x times x? So this is correct. 5x is correct. Earlier in a different class, they said it had to be 25x. But remember, anytime you're plugging stuff in, you have to use parentheses. So because we're squaring whatever A is, and that includes the 5 too, not just the x. So that squared is 5x times 5x, which is 25x squared. If I did plugging in 25x, then I'd have to do 25x times 25x, which is way more than 25x squared. I don't even know what 25 is, but it's too big of a number. All right. So that is good. Practicing substituting and seeing if it makes it true. I know with the first two, it made it look pretty much exactly the same. And then in the last two, they looked like different formats, but they were still equivalent because they were saying the same thing. When we have parentheses raised to a power of 2, if on the inside is like multiplication or division, then that can be, I guess, distributed in a way to everything. So it is like 3 squared and x squared. But if it's an expression like this, and it's squared, you can't just distribute it in that case. So if it's like plus or minus in the parentheses, you can't just look at this and say that it's x squared plus 16, because it's not. Right? You have to do x plus 4 times x plus 4, and then you end up getting a trinomial. The only way that it cancels out that middle term is if it's a difference of squares, which we did last Friday, where one of them has a plus and the other one a minus. That's the only time that the middle term cancels. If you have an expression like this squared and you multiply it out, you should get a trinomial. And that's a really common mistake. That's why I'm done. You can only apply the exponent to everything inside if it's like multiplying or dividing inside, not when it's adding or subtracting. So when in doubt, just write it times itself, and then you can't really go wrong there. Questions? Okay. So reason why we are doing this is because we have to be able to identify perfect squares. Sometimes it does make it easier to solve than like factoring, for example. And on your test, and you can look at the study guide to know what I'm talking about, you will be assessed on identifying perfect squares. So specifically of linear expressions, which I know like throws people off, that word linear. This x plus 4 is an example of a linear expression, because it's like mx plus b. A perfect square of a linear expression would be like this, that now is a linear expression squared. Or it's the same exact parentheses times itself. And in each parentheses is a linear expression. I know that throws people off, but when I multiply it out, it creates a quadratic. That's true. But what's being squared is a linear expression. You have to be able to identify if it's a perfect square. Different from difference of squares, okay? Don't get the two confused. I'm recording right now. I update the lesson every year. You can work ahead, you can work backwards. There's still plenty of time to catch up if you're behind. The practice is lesson 11. And the study guides have been made available. Some people, like the reason why their letter grade is not where it should be, like there's people that are doing better on the tests, but like because they have a bad project grade, they're like down the whole letter grade. If you need to make up those project points, do the extra credit IXL skills for Unit 7. It'll help prepare you for the next test, and it'll make up for those lost points. So there's that. We're about halfway through, maybe a little more than halfway through. So like I said, in that message on Parent Square and like every day when I talk to you now, we are almost to the end. You need to finish strong. For like the next 2 weeks, there's only homework grades going in the grade book. So like your grade will not change very much for like 2 weeks. But then there's like all these project points, all these assessment points, your final exam, like you need to finish strong. You need to be ready. Today I have tutoring till 3. Tomorrow, Saturday Academy. You could ask questions on the study guide for Unit 7, like whatever you need to make sure you're ready. But there's that. Questions? Okay. So now you are going to, in the next activity, you're going to write these expressions in standard form. So standard form of a quadratic will look like this, ax squared plus bx plus c. But sometimes you don't have a b term, sometimes you don't have a c term. You have to have an x squared term because otherwise it's not quadratic then. But when we say simplest form or standard form, really what we mean is like fully simplify it. Multiply everything out, combine like terms. Ideally, it would go like in the ABC order, descending order of exponents. Usually it ends up like that anyway when you're multiplying. But these are all in factor form. Write the equivalent expression in standard. You can move that 5 minutes to do that. Table 8, what is this first expression in standard form? When fully simplified, what does it equal?
Max with.
All right, do you guys agree with that? So remember, what do exponents tell you to do? All of you can answer this. You should be able to answer it. I ask you guys almost every day. What do exponents tell you to do? Not just multiply, like I'm not going to do 3x times 2. Finish the sentence. Multiply the base by itself. So this over here is the same thing as writing 3x times 3x. And then class is 3 times 3, 9. Is x times x, x squared? Then yes, that is correct. And because in the parentheses is only like multiplication, you could like do the exponent rule that says if you have something raised to a power, it goes to everything inside, but that's only for stuff like that. For C through F, you can't do that, okay? So that one's correct. Table 9, what about the next one? What does that one look like in standard? Okay, good. Right, 7 times 7 is 49, x times x is x squared. Fully simplified. Table 1, what about this one? Fully simplified, what would it equal? Okay, let's stay one step at a time then. We'll do FOILing because it takes less scratch work. So table 1, multiply the first term in each parentheses. What's x times x? X squared. Now multiply the outer terms of the problem. What's x times 4? Now multiply the inner terms of the problem. 4 times x is. And now multiply the last term of each parentheses with 4 times 4. Good. And truly standard form would be fully simplified. So then we just combine the like terms in the middle. And this is our final answer. So 4x plus 4x makes 8x. Now notice this one has, it's still considered a perfect square because it's the same parentheses times itself. And it creates a trinomial. All right. Difference of squares, which we did last Friday, has one of them as plus and one of them as minus, and that's why it doesn't create a trinomial. So, just keep that in mind. If it's a perfect square, you should have a 3-term for the standard form. Table 2, what about in D? What's my standard form for that one? X squared plus 2x plus 1. If you were thinking that this one could be x squared plus 1, then you are wrong. I'm trying to steer you away from that common mistake. It creates a trinomial. There's a perfect square. You cannot just distribute this exponent when there's addition or subtraction in there. You can't. So what it is before we combine like terms, so like we expand it, that's what we do. The first terms, the outer terms, the inner terms. And then my last terms, and then combine like terms. This is correct. Table 3, what about the next one? Okay, I might have heard you. Can you start over? Oh, okay. 2x squared. Oh, okay. All right, x squared. Okay. So then in this one, we're almost completely right. I just think maybe we multiplied the -7 and the -7. Right, but first we have x squared minus 7x minus 7x plus 49 is -7 times -7, so just adjust that. But otherwise, like the rest of it was good. Find like terms right, and make sure to expand it before multiplying it. It should have a 3-term in the end. And then lastly, the one with the variables, still the same process. Table 4, what about this last one? X squared plus nx plus n, is that what you got? Okay. So in this one, it's x plus n times x plus n, that's what the exponent tells you to do. The first terms multiplied together is x squared. The outer terms is nx, and we do like to put it in ABC order, so that's why I'm doing nx instead of xn. Multiply your inner terms, you get nx, and multiply your last terms. What's n times n? N squared. So let's adjust this. It should be a 2nx for the middle term, because we had 2 of them. They're the same exact variables with the same exact exponents. They're both n to the first and x to the first, so we can combine them. 1 plus 1 is 2. And then that last term is n squared, because we're multiplying. Questions on that? Now, this one is good for like revealing a certain rule that you could use and memorize to identify perfect squares. Personally, I just like to, like, if they gave me the standard form, I just like to factor it and see, like, does it give me something times itself? Does it give me the same exact parentheses? Then I know it's a perfect square. I like when I study to memorize as few things as possible. But this is like a good observation to show you like the pattern between them. Anytime that something is what we would consider a perfect square trinomial, has the first term as a perfect square The last term has a perfect square, right? 49, 1, and 16 are all perfect squares. And then the middle term for each one is always 2 times these square roots. So like, take a look at this one for example. Everyone's looking up here. What's the square root? Well, first let's do the 2. What's the square root of x squared? What's the square root of 49? And what other one was it? I think it worked last hour, but isn't the 14 2 times x plus 7? Isn't it? 14x is 2 times x plus 7 or times 7. So that is our perfect square trinomial then. To recognize it just based off that. If you see the first term and the last term are perfect squares, and that middle term is 2 times the square roots, you have a perfect square trinomial. So then look at this one. What's the square root of x squared? Guys, open your eyes and answer the questions. What is the square root of x squared? What's the square root of 1? Isn't 2x 2 times x times 1? And then now look at this one. What's the square root of x squared? What's the square root of 16? 4. Isn't 8x 2 times x times 4? So that is another way to identify it just from the fact that it's in standard form and the first term and last term are perfect squares. The middle term is always 2 times the square roots, then you have a perfect square. But really, I prefer to just factor it and look at my top group. This to me is easier to identify my perfect squares than going through all of that, but it is a time. Questions on this one? Okay, so what I mean by that is if I'm trying to see if this is a perfect square, what I would do is I'd factor it. So there's no GCF, it's a trinomial. I'd set it up like this. A times C on the top, B on the bottom. So 9 here, 6 there. What 2 numbers multiply to 9 but add to 6? 2 numbers. 3 and nope.
3.
That's 2 numbers. So 3 and 3. Do that. 3 times 3 multiplied to 9. They add to 6. My factor form would look like this. And it's the same exact parentheses times itself, down to the signs and everything. So because it is the same exact parentheses times itself, I can write it like this. It is a perfect square. That trinomial we'd still call a perfect square because the factor form is a perfect square. Make sense? So prove that the other 2 are perfect squares by factoring. To me, this gives you less things to have to memorize because you already have to know how to factor. So if you're asked if it's a perfect square, just factor it and see from the factor form, is it the same thing times itself? Give you like 2 minutes. Okay, so table 9. We're proving that it's a perfect square, the trinomial, by putting it into its factored form. How would I set up my diamond? What would go on top? And table 1, what would go on the bottom of this diamond? Close, negative 16. Because you have to keep the sign that's in front of each term. But Yeah, you have to be able to set this up correctly in order to use this effectively to identify your perfect squares. Now, I know 64 is a perfect square. What's the square root of 64? And 8. And to make it add to a negative 16, they both have to be. So yeah, because it makes it work, multiplies to the top, adds to the bottom, it creates the same exact parentheses times itself. This is a perfect square. That trinomial is a perfect square. And then the last one, just because it has a fraction, doesn't really change anything. You can use your calculator to handle some of the fraction calculations. But we're trying to prove that this is a perfect square by factoring it. So to set it up, my a times c, 1 times 1 over 36 makes this the top number. And my b term, the bottom number is 1/3. We're looking for numbers that multiply to the top and add to the bottom. And for the perfect square method, ideally it would be the same numbers. So hopefully you know your rules for multiplying fractions. You just multiply straight across. So what times itself will give me 1? Or what I hear? 1. My numerator would have to be 1 then. What times itself will give me 36? 6. And I do think, like, if that's so hard for you, I do think the calculator will work for square rooting it, that fraction. If I square root 1 over 36, it'll tell me the decimal, but I just press this button and it gives me the fraction. 1/6 times itself gives me 1 over 36. Now, 1/6 plus 1/6, you could use your calculator for that too. 1/6 plus 1/6 is 1/3. All right, so also I could have just shown you that. I know my fraction rules, but this is how you can check yourself. Because you will have on your final a question that has fractions, and you can't just like skip it on the finals, where it's a big chunk of your grade. 1/3 is what it equals. Simplify it. So yeah, my parentheses for this one would look like x plus 1/6. Or really, like, we usually slide any remaining denominators in front, but they're the same exact parentheses times itself, so it is a perfect square. And you could write it in your own words for how you know that something's a perfect square. If in the factored form, it is the same exact parentheses times itself, it's a perfect square. Not to be confused with the difference in squares. They would be different. But perfect squares is the exact same times itself. Good. Any questions? All right. Here's a definition for perfect square. Again, you should be able to give one for yourself. It's an expression that is something times itself. Something times itself. By the way, these are all examples of linear expressions in the parentheses. So this is a square of a linear expression. All right. Now, being able to see that there's a perfect square of a linear expression helps you in solving sometimes. So like take a look at my screen or your paper, it's on the paper too. Han and Jada solved the same equation with different methods. Here's what Han did. Based on his scratch work, what method did he use for solving? We only know a few methods so far, so What does it look like Han did to solve? Well, he did have to FOIL it out over here because he eventually needed it to be set equal to 0. And he had to subtract that 25 on each side. So here's where he set it equal to 0. And then he factored it. Yeah, so he solved it by the zero product property, or by factoring is what we, like solving a quadratic by factoring is what we usually say. And that's a lot of work, isn't it? He has to multiply it out, he has to do inverse operations to make it equal 0. Then he has to factor it and then solve for the x's. It gets him the right answer, but takes a lot of steps. And there's, as you saw, you do one wrong sign on one of the steps and then the whole problem's thrown off. Now look at Jada's method. Hers has way fewer lines, and it is still a reliable way to solve it. It's like what we did earlier in the unit when we just isolated the variable. So here's a perfect square. Because it's written in the condensed form, we can isolate the variable a lot easier than what Han did, right? Because we just isolate it. What's opposite of squaring, class? Square rooting, so whatever is the one side, we keep the other sides. That creates just the x minus 6 on one side. And on the right side, what's the square root of 25? And remember when we were isolating x before, it's now plus or minus 5 when we're solving. And that's where you can see in the next line, she broke it up into 2 separate problems where it's equal to the positive 5 and equal to the negative 5, and then solved those. So a lot fewer steps. If you see that that can happen, probably more effective and less likely that you'll make a mistake. But as long as you're getting the right answer, do whatever method you want. But on your tests, like you have to be able to say if someone made a mistake, what the next step would be based on how they solved it. So that's what I'd be trying to stress to you. It's not just gonna ask for what X. So up to you. I would encourage you to use Jada's method on these. Down here, practice solving using either method, up to you, but like I encourage you to do Jada's because it's a lot shorter. And really we'll only have time to go over a couple of these. So let's go over this one and that one. So do these first, and then if you have time, do that one, but practice solving using whatever method you want other than graph.
Table 3, what would the first step be in solving the first one?
Square rooting, because we see, like, unlike other ones that we've had to solve, there's only one variable because it's written in the condensed form. So I just have to square root each side to start isolating the variable. That eliminates the exponent of 2. That gives me just the y minus 5. The parentheses can go away now that there's nothing else on the outside of them. And class, what's the square root of 49? And let's put plus or minus 7 whenever we're doing a square root and solving. Put the plus or minus, because there's usually 2 answers. Table 4, what would be the next step? How do you fully isolate the y? Add 5. Whatever you do on one side, do to the other. You could have, at that stage that I wrote in black, set it up to 2 separate problems, like here how Beta did it, if that's easier for you. Personally, for me, it's easier to just remember to do the positive 7 plus 5 and then the negative 7 plus 5, but up to you. Class, what's positive 7 plus 5? Well, what's negative 7 plus 5? What did you say, Wade? All right, guys, we still have a whole nother activity to get through. Me asking you simple addition and subtraction needs to go a lot quicker. Questions on this one? And notice that I'm not using parentheses because parentheses we use for coordinates. This is not a coordinate. This is me saying that y could be these numbers and nothing else. So this last one that I asked you to try, table 5, what would be the first step? Square rooting, because that's farther from the v, so do the opposite of squaring, which is square rooting. We get it to be v minus 0.1 equal to the square root of 0.36. I would recommend just use the calculator for that. Even I tried doing it in my head earlier and I was thinking it should be 0.06. But actually the square root of 0.36 is 0.6. Okay, so there's that. 0.6 is my square root. And because we usually have two answers, you need to remember to put the plus or minus 0.6. Table 6, what would be the next step? How do I get the v fully by itself? Add 0.1 to both sides. And then we get v equals, and you could split it into two separate problems if you want. But since most of the time there are two solutions, that's why that plus or minus is super important, because we need to do positive 0.6 plus 0.1. What's that equal? 0.6 plus 0.1? 0.7. And now do negative 0.6 plus 0.1. What is that? Negative what? Negative 0.5. Those are my two solutions for that one. All right, so if you had this, but like maybe a step was missing, could you fill in the missing step? Following the algebra, undoing what's being done, doing it to both sides, not forgetting the plus or minus. Hope so. Last thing we'll do today, which is also really similar to what you'll see on your test, is the next activity underneath that. The one that says, what are perfect squares? You have 4 listed. Be able to tell me which, if any, are perfect squares and how you know. So which, if any, of these are perfect squares and how do you know? This will be the last thing we go over. If you are just waiting for us to go over it after you tried it, do your practice, don't pack up until 10-20 minutes. We're definitely answering this, so you need to take notes.
Which, if any, are perfect squares? Show me with your fingers. Let's do like, this will be 1, this will be 2, this will be 3, and this will be 4. Show me with your fingers which, if any, you think are perfect squares.
Okay, mostly just see 2s, so let's try it to confirm. To me, the easiest way is to factor it and then look at the factored form. So if I was factoring it, I would do 144 on the top, 24 on the bottom. And we'd like for it to be, if it's a perfect square, the same numbers here. So what's the square root of 144? And does 12 and 12 add to 24? So my factor form would be x plus 12 times x plus 12. That is a perfect square because they are the same thing times itself. Were there any other perfect squares? Yes, 4 was the other perfect square. Because for that one, if you factor it, we can to make it add to a negative 40 on the bottom, these would both have to be negative 20 right here. And because it's the same thing times itself, that's a perfect square. The other ones are not, like if we tried, first of all, I can't think of any numbers that multiply to 8 and add to 4. So this one I think is times and no numbers that. So definitely not a perfect square then. And then this one over here, 16 is a perfect square, but 4 times 4 does not add to 6. Right, so that doesn't work, it makes it not. The second and fourth one. That's fun. Oh, wait,